So today, we are going to talk about a particular property of a circuit called the current, all right? And you can see here I've got various devices here. Again, I've got my battery, which is our source. I've got my lamp, which is the load. And then I've got the conducting wires. And again, I don't use a switch because I can just make a switch simply by opening the circuit. And I can then connect these two. And am I getting even anything there? Oh, there we go. Ooh, we're blinded by the brightness of our bulb. That's okay. So we have some electrical energy that is starting here in the load and ending up being turned into light at the, starting here at the source and ending up being turned into light at the load. There are a couple of properties of electrical circuits that you may know. One, we've used the term voltage, and that's an energy value, and that's our tomorrow's lesson. And the second important property is how quickly the charges are flowing through the circuit, all right? And this flow of charges through the circuit, we call the current, all right? And it's based upon the historical view that scientists thought that there was actually a fluid flowing through the wires instead of what we know now, electrons, little charged particles, moving through the wires, all right? So we still use this term current as if it's some kind of flow of fluid. You can imagine it almost as being water flowing through the circuit. Now I'm going to change your view of that. I want you to think of it as electrons instead of as a liquid. So keep in mind, we've got electrons flowing. I'm going to shut that off so it doesn't kill it completely. So let's define what we mean by electrical current. Oh, sorry, no. Before we get to talking about electrical current, let's talk about the electrons flowing. And then we'll get to the calculation. So which way does the current flow? Now I did a motion kind of like that. But why couldn't it be the other way around? Well, there is a reason, and there is a certain direction. Again, you can see there's a circuit diagram there, and I've got a couple of cells here, two of them, in fact, connected together. That would be like me connecting two of these cells together, which I'm not going to do. And I've got my connecting wires, which are represented by just those lines. And then I have a load over on the other side, represented by these squiggles. What type of a load is this represented by the squiggles? Those of you who wrote down your circuit diagrams, what is that particular thing? Yeah, Jewel, what do you got? It's pronounced a resistor, all right? So it's a resistor, and I'll be explaining to you more on what a resistor is, all right? But it's a load. It'll turn it into heat. All right, remember the last day? I indicated to you that on our cells, we have a short line and a long line, and that short line reminds me of this symbol, and that's how I know which end of the battery or the cell it is. Does anybody remember what the short line represents? Yep, Jess? Oh, 50-50. Don't go buy a lottery ticket today. Try again, Harrison. The negative. Negative there, positive there. Okay? All right? Now, the law of electrostatics still comes into play here. If there's an electron in the wire close to that negative, how is it going to want to move due to the law of electrostatics that we learned? Danton? The negative electron's going to want to move closer to that negative end of the battery? No, they want to move away because they're going to be repelled away. So all of the charges that are in these wires, and they're kind of hanging out, ready to do something, are going to start to repel away from the negative and be attracted in to the positive. So that's the direction in which we imagine the electrons flowing, all right? So the electrons are negative, they're going to repel away from that negative electrode and be attracted through the wires towards the positive electrode, okay? We're okay with that? Okay. So our electrons travel out from the negative towards the positive. All right. Let's now talk a little bit about different types of current. And I mentioned this yesterday, and I just want to officially put it in the note for today. Oh, and look at what I did. I turned that circuit upside down. Everybody see that? I don't want that to be upside down like that. I'd like it to be the same. You know what? We can leave it. We're smart enough to think about that. We can figure it out. I haven't used this note in a while, but I don't know if you noticed. I've got my battery here flipped over compared to the last picture, but that's okay. This is representing a graph of how the current is going to change with time. So, when I connect this battery to this lamp, the electrons are being repelled out of the negative, which is the black, and towards the positive, which is the red, all right? And they're all flowing in the same direction, around and around and around, all right? This is DC electricity. It stands for direct current, and direct simply means it always flows in the same direction. Again, this is our negative and this is our positive, and therefore it's going to repel out, going the other way, and come back in, always heading in the same direction. So if I had a certain value for this current, which we're going to give it a number in a moment, let's say 2, it's always going to stay at 2. It's never going to get lower or go backwards. It might get lower when the battery dies, so it might slow down, but it's always going to go in the same direction. So it's going to have a graph that's flat like that. Always at a value, of example, say 2. Always in the same direction. Okay? Batteries produce direct current. They always head in the same direction. Okay? That's why yesterday when you made your cells out of the 2 half cells, we had to set the device to the DC setting because we were measuring DC. Okay? Y'all are getting our note there? Good, let me know. Things that use DC, I just want to finish off. Sorry, things that produce DC, yep. Yep, the symbol for DC, well, the symbol for DC is just this type of symbol. So a DC source is our regular symbol for a battery. That's our regular battery symbol. Why? Because batteries produce DC. Okay? So the DC symbol is just a regular battery symbol because batteries produce DC. Okay? All right, so things that produce DC, well, batteries. Cells, batteries. You might say that, isn't a battery the same as a cell? Technically, it's not. Each single chemical unit that we made yesterday is a cell. When you put more than one cell together, that is what we technically call a battery. This is one single unit. We call them batteries, but it's technically a D cell. It's a single chemical system. So this is technically not a battery. This is technically a cell. If I connect 2 of them together, like that, I've created a battery. It's a battery of cells. 2 cells in a battery. So don't worry about that right now. I'll show you some examples of some different ones later, but that's the technical terminology. Other things that produce DC. Well, if your phones use DC because they use batteries, then you have to charge your phone with a device that produces DC that goes in one direction. What do you use to charge your phone? Yep. A charger. A charger. Now, back in the day, we had a special name for that type of a charger. Does anybody know what that is? You guys just call them chargers, but there was a name we used years ago. USB is DC, right? So USB uses DC, 5 volts DC. But no, it goes even back further than this. We used to call them adapters. Have you ever heard that term before, an adapter? Yeah. Notice, see my smart board's plugged in with that funny black thing into the wall? You'd have to stand up and see it if you want to stand up and see it. But that's got a cord that goes into my smart board. That's an adapter, all right? So we'll just call them, phone chargers, all right? We'll call them phone chargers. Phone chargers. And I'll put the 5 volts USB, all right? Oh, sorry, not USB, USB. Universal Serial Bus, I think is what that stands for, but don't worry about it. All right? Things that use DC. Well, anything that uses batteries. What do you got? DC uses. Yep. Like a toy that runs on batteries, like a toy car. Yeah, I like that. Toy car, you bet. But what's that? Oh, a Walkman. Yeah, they did. They were cool. I still have one in my garage. Don't make fun. All right, yep. What's that? A phone, for sure, phone. Now, you guys, it's funny because you guys, again, I think back to the last time I taught this, and not everybody had phones. Hardly anybody had phones. So you didn't have that nice bright light on the back. So us old people, if we wanted to see in the dark, what did we use? Yep, a flashlight. You guys never use a flashlight anymore. Nobody has flashlights. All right, a flashlight. Yes, correct. I guess that's it. Yep. Is that like, are you saying like before electricity? My goodness. Okay, I'm going to keep going. I'm going to go on to the next slide while I'm just going to go on to the next slide while you guys get caught up. But I'll be okay. You know, Rachel, sometimes I go home and I cry. I'm just saying. Remember when Rachel came in and could hardly look at me? What has happened to those good old days? What happened to those good old days? I know. I gotta somehow crush the confidence out of her somehow. I'm not sure. Okay. Let's continue. Alternating current. Shh. Let's focus. Focus. Alternating current. The electric charges change direction periodically. Now, when we say periodically, we don't mean the way common people might use the term periodically. Common people might think, oh, once in a while it decides to change direction. That's not what we mean. When in science, when we say periodically, we mean it's very regular. There's a very regular change in direction. So it goes forward for a certain amount of time, and then it stops, and then it comes back and goes actually in reverse, right, for a certain amount of time, and then goes forward. Generating stations use a generator that creates AC, alternating current. That hand generator that I produced, or that I showed you the other day, was producing direct current. That generator could produce direct current. But the big generators, hydroelectric, nuclear, et cetera, produce AC. Here's our symbol for AC, and it's got a wave on it. And that wave is called a sine wave. You'll learn about it in math. And that represents how the current goes forward and then reverse. So our graph for current this time is forward for a while, then in reverse, then forward, then reverse, then forward, then reverse. Okay? And the way the generator is built, it makes that perfect, nice little curve that is not supposed to be growing, but mine is growing a little bit. It's not supposed to get bigger. Yes? Per second, correct. That's how quickly it goes back and forth. Yeah, it's got a very definite period, but it's very fast. You're right. So this is our symbol for an AC system, and that wave represents the wave of the current going back and forth. It wiggles. It vibrates and wiggles in the wire. This is called a ticker tape timer. This is a particular type of timer that we use in physics to measure speeds of things. All right? It simply has a magnet in here that every time the electricity goes, that this hammer goes down, and then when it stops and gets to the middle of our graph, it lets go, and then when it goes the other way, it makes another noise, which means if I plug this in, we're going to hear what 60 times per second sounds like, and it sounds like this. It sounds like this. Now that's kind of annoying. It's designed to make that noise. But if you listen very carefully to things like your refrigerator motor or other things that have motors in them, they will make that sound because they're also vibrating at that same rate. All right? I don't think you can hear it with the fan running, but when I turn on the gas jets, there's a hum up in the ceiling. Because of the fan, you can't hear it. It's 60 hertz. Okay. We are not going to be using AC because it's dangerous. It has a lot of volts and can produce a lot of current. And so we are not going to be plugging things into outlets unless they're plugs that are designed to be plugged into outlets. We will be making circuits, though, using devices like this. Things that produce AC. We're going to say home outlets. All right? And ultimately, that comes from the generators that produce that. I think we'll just leave it at that. There probably are some others, but we'll just leave it as that, home outlets. Things that use AC, anything you plug in. Anything you plug in to one of those home outlets. Yes?
But if a phone charger is AC, but you plug it into like a
There's a special little circuit inside the phone charger that turns the AC into DC. And that's why, no, an inverter goes the other way around. Inverters turn DC into AC. That's an inverter, all right? An adapter, which is what we used to call them, turn AC into DC. Inverters go back, all right? So if you have an inverter that you plug into your car, the DC battery, the car battery, it'll turn it into AC so you can plug in your game, whatever. That's an inverter. That goes back the other way. Okay? Because a car's battery is DC. Okay? It goes back. There's a circuit in there called a rectifier, and it turns the AC into the DC, which then can go into your phone. Yeah.
Since AC uses more power.
It's more powerful. It doesn't necessarily use more power.
But when you transfer it to DC, where is that?
So we have electrical components in it that can change that high power to push out just a little bit of power. Things like resistors do that. It eventually, it sometimes just goes into heat, which is why your thing gets hot. because it's dissipating some of that power into heat. Yep. Oh, well, that's because I copied and pasted this a million years ago. Yep. Last question. It has to do with their size. It's a size designation, and I don't know why smaller ended up with more A's. I don't know where the origin of the lettering system for cells originated. Okay, now we're ready to calculate current. Current is a measure of the number of electrical charges that passes a point each second. So, if I put in this battery, and the battery begins to, or the lamp begins to light up, and this battery might be dead, doesn't matter. As the electricity flows, it flows at the same speed throughout the circuit. So I could measure it here in the black wire, or I could measure it here as it enters the lamp, or I could measure it here as it exits the lamp, or I could measure it here in the wire, or here as it goes into the battery. But everything moves like a train. It's always going the same speed in the circuit. Okay? So as soon as you connect it, all the charges are moving around like a train. All right? So I've given you your first equation. I is the symbol for current. That's what we want to calculate in our equations. We also might want to calculate the other things. And that current is measured in a unit called amperes, or amps for short, named after a scientist by the name of Ampere. That's why we use a capital. Q. The Q stands for the charge, the number of charges going by. We can't count individual electrons because they're too small. So we put them in these big groups, and I already mentioned it to some of you when we were talking about static electricity. We put them into these big groups called coulombs. And it's in C, a capital C, named for a French scientist by the name of Coulomb, or something. I don't know, I can't say it like from French or anything like that. It's a big number. To be honest, I can't remember what it is. Somebody could Google it for me. How many electrons or how many charges are in a coulomb? All right? Coulomb is C-O-U-L-O-M-B. T. Because this is how fast it's going, the charges are like the train cars, or I like to think of them like dump trucks. And T is the time. How long it takes for the coulombs to go by. How many in a coulomb? Times 10 to the 18 electrons equals 1 coulomb. Is that, we got that on it? So there's a lot. There's a lot of electrons in a coulomb. Yep, but they're small, so we put them in these big bunches. Time is measured in seconds. Okay? So an amp is telling us that a coulomb is going by each second. 1 amp, 1A, is equal to 1 coulomb per 1 second. So 2 amps would be 2 coulombs going by per second. All right? Now, when we measure amps, sometimes they are in milliamps, or sometimes we have to go back and forth. Now, we did some conversion earlier on, and I tried to get you to do this with powers of 10, but I'm going to show you an easier way. There is 1,000 milliamps in 1 amp, just like there's 1,000 millimeters in 1 meter. It's exactly the same. So if I have 250 milliamps, How many amps is that? How many amps is that? Tristan? 0.25. How did he get that? Well, we have to divide this number by 1,000 or move the decimal over 3 spots to get us to 1. So I have to do the same with the milliamps on the 250, and that gets me to 0.25 amps. Okay? So how many amps is 1,300 milliamps? Kyla? How many amps is 1,300 milliamps? 1.3. You were just resting your brain there for a moment, right? That's right. Oh, nice, good. How many milliamps is 1.2 amps, Danton? 1,200. Okay, so we may have to go back and forth, and that's a 3-stepper, I always say. That's the 1,000, the 3 zeros. Okay, now we're ready to do our calculations. We good to go? Are you sure? Yeah, don't want to rush through. All right, so here we've got a problem. And you got to write them out. It's just the way it goes. You didn't get the last one? Boop. Let's get the last one. There we go. By the way, this says 585 coulombs. It's not 1.585. This is question number 1. You see what I'm saying there? Question number 1, space. Gotcha. And I'm not doing anything magical here in these questions. I'm really just making them up. I'm not getting this from a real circuit. I'm just writing numbers down and getting us to think about it. So we are beginning to gather up our equations. By the time we're done this particular little unit, we'll have about 5 equations. I equals Q over T. The best way to do these is to recognize the units. I is in, and what's the symbol for current? What's the symbol for the unit for current? In other words, if I'm looking in the question, what am I looking for as a unit? Yep. Amps, A. I'm looking for A. Q. What's the unit for Q? What's the unit for Q? Chloe? C. And what's the unit for T? Yep. Nope, it's not minutes. Seconds. Excellent. Let's start writing our information down. When you have a question like this, the first thing you want to do is take note of your information and figure out which of the letters it is before we put it into the equation. So, the 585C, what letter in my equation is that going to be? What is the 585C? Yep, it's the Q. So I write down Q equals 585C. And I have it in the correct unit, which is a good thing. 1 minute. Which of my symbols in my equation is the 1 minute? Yep, it's a T. But now I'm concerned because do I put minutes into that equation? No. What do I have to do, Danton? And how many is that? 60. So as I'm making my list, I'm making sure everything's in the right unit. Okay? What am I looking for in this particular question? Yep. I'm looking for the amps, which means I'm looking for I. I equals question mark. And I like to put that in my list. I equals question mark. Well, my equation is already rearranged for it. All I got to do is put things in and calculate. If you see what I need to do here, don't wait for me. This is the type of thing that if you know where you're going from here, go ahead of me. And then if you get it right, you can say, yeah, way to go, me. I did a good job. Use a pencil if you're going to go ahead of me. Because then if you make a mistake, you just erase it. Don't worry about it. No big deal. All right? I equals Q over T. 585C over 60 seconds equals. This is where we want you to participate. Play the game. We're waiting because I am going to wait for Parker to get his phone or whatever calculating device he has. Do you have a calculating device, Parker? Here, I will supply you with this calculating device. There you go, sir. Again, it's very important that we all put this in the calculator. This is a participation sport. Because you have to know that you know how to put the numbers in the calculator to get it right. It's super important. What do we have? Marshall, you got a number? 9.75. Do we like it? Because I'm not calculating it. Supporters? Excellent. What unit goes with the letter I? What unit goes with the letter I? Yeah, Allie? Oh, that would be correct. But we have the other symbol instead. Amps. A. We use amps. But you're right, it is coulombs per second. Yes? Yep. Do you get them on the test? Let's worry about that later. Let's worry about that later. Let's not worry about that right now. I haven't decided. 5.7 times 10 to the 7 coulombs of charge pass through a tree in 1.5 seconds during a lightning strike. Now, even though that's not a regular circuit, that's, a thing that we could measure. It is DC electricity. Determine the current. Again, once you're done writing the example, don't wait for me. Start making a list of your information. Figure out what you're trying to find. And then get your equation. Now, you'll notice we've got some scientific notation. So I'm going to be teaching you how to use your calculator and what buttons to press in order to put that in your calculator. And by the way, you don't actually press the times button when you do this. So that's why I got to train you a little bit. (5.7 times 10 to the 7c). What is that in my equation? Which of the symbols in the equation is this going to go as? I'm going to pick on people. Are you calculating already, Parker? You can be. Are you? What do I put with this, Parker? C. What is the symbol in my equation that goes with the C? Q. Nice. 1.5 seconds. What's the symbol that goes with seconds? Parker? T. And therefore, what are we looking for? I. Question mark. Look at the way I made the list this time. I simply wrote the number down and then I thought about what that was. Doesn't really matter how you do it. Our equation is I equals Q over T. I equals Q over T. 5.7 times 10 to the 7c, 1.5 seconds. All right. Calculator training.
Excuse me, Mr. Sands, can I please have Rachel Wood to the office to find out?
Yes, with pleasure.
Thank you.
You're dismissed. By the way, there's a worksheet on this, and I want it handed in tomorrow. Oh, no, I'm being nice to you. It can be handed in on Monday. Anyway, go ahead. All right. Calculators ready, ladies and gentlemen. Goodbye. You are looking for a button on your calculator that says EE, or it might be EXP. Can you find that button on your calculator, EE or EXP? Some of you may have a calculator that writes it like this, 10 or times 10 to the X or something like that. I hate those calculators. You need to find EE or EXP. If you don't have it, you can't do the calculation. Have we found the button? It could be a capital E, capital EXP, and it could be a second function. It could be up above, a button. Do you see it? See it? Everybody seeing EE or EXP? Chloe? You found it? Good? We got it? Have you got an EE, EXP? Yep.
We're gonna want to make sure that you have so long.
Yep, no, but you're not, have we found the button, EE, EXP? Found it? Found it?
No, my phone is from me. Well,
Okay. You can take that one.
thank you.
Okay, here's how it works. The EE or EXP button, depending on your calculator, it stands for times 10 to the blank. It's got the times built in. So here's how it goes into your calculator. Everybody following along? Press 5. Now press the dot. Now press 7. Don't press times. Press the EE or EXP. Now you'll notice up in the upper right-hand corner, your calculator might have a little times 10 to the up in the corner. Do you see it? No? If it doesn't, that's okay. Now press 7. Excellent. Now press the divided by button. That looks like this. Now press 1. And then the dot. And then the 5. Now press equals. Now, your calculator is going to maybe have a funny notation there, or it might have something that might have a lot of zeros behind it. I don't really care which one it is. One of yours, they might have a little scientific notation up in the corner. Tell me what your calculator says. What does your calculator say? Just tell me the zeros. Oh, so tell me the first numbers. 3, 8. 1, 2, 3, 4, 5, 6. Is that what we got? What's the unit for this? Amps. Some of your calculators might say this. 3.8 times 10 to the 7 amps, which kept it in scientific notation. I don't really care which one you give me. Remember how we did scientific notation at the beginning? Those are the same thing. Are we okay with using big numbers if we get them? Awesome. Let's do one where we have to rearrange an equation. Oops. I said I didn't want to hear yay. This is fun stuff. Science is math. Okay. To be honest, and this isn't the proper way to do questions like this, but I scan the question and I'm looking for units. I'm looking at the units on the numbers. That allows me to get to the question quickly. Again, also, as you're writing, you're reading it, so you can see what the units are. But if this is on a quiz or a test, I'm scanning that and I'm seeing the letters that are in the units. And I'm asking myself, what is that telling me? The first, I'll let you write. I'm getting ahead of myself. Getting all excited. This is the fun stuff. This is the fun science. It is. .28. What is that in my equation? Which of those things is that in my equation? Yeah, generally, I. You're telling me the next thing?
No, I have a question.
What do you got?
If we have this one said, do you have to actually like 5.2a equals I? We actually have to write all of it. For 10 years.
You guys are lucky that you have me as, listen to me, listen to the way I'm saying. You guys are so lucky to have me for a teacher. Many grade 9 teachers are very picky about the way they write that. They give marks for that.
Yeah.
I've taught physics for years. To be honest, if you get it in the right spot and you show me your work, I don't get that excited about it. But it's good practice if you're not sure what to do to write your information out, all right? So let's say you're in a hurry, you got like one more last question and you quickly do it, but you don't write it out, I'm still gonna give you full marks. You see what I'm saying? And some teachers get very picky about that. No, it's good practice. What you're being taught, that is good, it's called good practice, all right? And I'll even do this when I get a problem that I don't know how to do. Let's say I'm given a new problem and I got to work through it, whether it's something that I've got to do myself or, you know, or for a student. If I'm not sure what to do, I always default back to this because this then allows me to think through about what's happening. Hello.
You have a jacket?
Sure. Just for me? Nice. Thanks.
Well, we loved your costume.
Awesome. Thank you very much. Just chocolate for me. All right, let's keep going. 2.5 minutes. What do I want to do with this? Yep. And how am I going to do that?
Isn't it like 250 seconds?
No. Nope.
Sure?
Yep. What do I have to do to it? Yep. Yep, that'll work. What else could we do, mathematically speaking? Yep. Multiply by 60. Yeah. So 2.5 minutes times 60 seconds. What do we got? Yep. 150? And what symbol is that? Yep. T. So what am I looking for? Looking for Q.
Oh, exactly. What is
Okay. Q is the charge. It's in coulombs.
No. What is Q in this question?
Oh, correct. I equals Q over T. Substitute your information in. Whoops. I don't have erase. 5.2 amps equals Q over 150 seconds. It doesn't work. What do I do to get the 150 seconds to the other side? Yep, Tristan? That's correct. I multiply 5.2 by 150. Different math teachers will express this differently. If they're doing it properly, they're going to say multiply both sides by 150. Does that sound familiar? So you can cancel out the 150 and then you've taken care of it. Other teachers will say opposite operations. Okay? It's a division on this side. It's going to be a multiplication on the other side. Okay, everybody, have you ever heard of that? I'm going to write this as times 150 times 150. That gets rid of that. Q is equal to 150 times 5.2. Yep. 780, and what's the unit? Just the letter is fine. C, coulombs. Okay? All right? That's all you do. That's all you do. Well, write it out. Now, other teachers will rearrange the equation. Let me show you one other thing. If I wanted to rearrange the equation first, I could multiply by T and multiply by T. Now, do you see how I'm doing this without using numbers? See how I had the 150 and I times by 150? Okay? So some teachers like to move the equation first, and then you have a new equation. Q equals I times T. What's that? Okay? Yep.
So for the, say if we have the top number.
Yep.
But we didn't have the bottom, would you still multiply or divide?
I'm not sure what you're saying there. Ask that again.
So now we didn't have Q.
Yep.
What if we didn't have,
T.
sorry, well, if we didn't have T, yeah, what if we didn't have?
I think I've got my next example is missing T. I hope it is. Oh, it's not. Let's make one out that's missing T. Let's make one up that's missing a T. It's a little different. No, it's a little different. If you're missing T, it's a little different. Let me stop the video and we'll do a T one. There's a worksheet there, and my plan was to have the quiz tomorrow, but that's not going to happen. But let me just stop this video for a second.